Hello friends, welcome back to the online classroom. Today we are going to discuss practicals on single stage FET amplifier, that is common source field effect amplifier. So here is the circuit diagram for field effect transistor and field FET amplifier. So there is a same circuit diagram for single stage C amplifier and single stage FET amplifier. The only difference is this transistor. So instead of BJT, that is bipolar junction transistor, now we are using a FET, that is field effect transistor, BFW. All other circuit components are the same, that is two voltage divider biasing resistors R1 R2. This is the RD which replaces RC in C amplifier. This is RS, that is source resistor, which replaces emitter resistor in C amplifier. This is the source coupling capacitor, this is output coupling capacitor, and this is input coupling capacitor. So to this input coupling capacitor will give input signal. So first we will see how this FET looks like, and it is different from BJT. So here is the FET. So you can clearly see it has 4 terminals. So this FET has 4 terminals, and here at this side you can see the notch over here. So this has 4 terminals. So names are drain, source, gate and substrate. So 4 terminals are there for FET. So we will see how to identify these terminals. So now you can see these are 4 terminals for FET. So you can clearly see this notch. So going towards a clockwise direction from this notch, you can see, so the first terminal in the clockwise direction, so it is a source. Then so this is the source, this is notch, you can see, this is notch, this is source. Next terminal is drain, next is gate, and last one is substrate. So from this notch you can see in the clockwise direction source, drain, gate and substrate. While using this, we will need in the amplifier, FET amplifier, we will only need 3 terminals, that is source, drain and gate. This substrate terminal should be shorted with the source terminal. So source and substrate terminal should be shorted. So this is your terminal analogous to emitter of BJT. So this drain is analogous to collector of BJT, and this gate is analogous to base of the BJT. So now you are going to give a input signal to this gate, and output is collected across drain while the source is common. So we will go to the circuit diagram. So this is the basic construction of the circuit diagram. So here is the FET amplifier, FET transistor we have connected. So this is the same circuit diagram as we have seen earlier for C amplifier, common emitter amplifier. The only difference is this transistor. So instead of BJT we are using FET. All other components, that is R1, R2, this input coupling capacitor, this output coupling capacitor, source bypass capacitor, source resistor and drain resistor are common. So here at the input coupling capacitor we have given the input. So this is input from function generator. So we have the input of amplitude of 50 millivolts and frequency of 2000 hertz. So this is the input signal we have given in between gate terminal to source terminal. and we have collected output between drain terminal and source terminal. So input is given to gate to source and output is collected across drain to source. So we will be measuring the output on this CRO. So this CRO you already seen. So now we'll start with our observation table. So this is our observation table. You can see we have the input voltage of 50 millivolts and we have to calculate the output voltage V out for different set of frequencies. So these are the different frequencies we have to calculate the output voltage at the same input voltage. We have to change only this input frequency or frequency of the input signal. Then as earlier we have seen in C amplifier, we have just to calculate the voltage gain and gain in dB, and then we'll plot the graph of your gain, and accordingly we'll calculate the bandwidth of your amplifier. So now first we'll start with this 20 Hertz frequencies. So we'll set the frequency to 20 Hertz. So now we'll set the frequency to 20 Hertz while keeping your amplitude constant. Don't change the amplitude. So we'll set it to the 20 Hertz. So now we'll calculate the frequency output signal. So as we reduced the frequency, you can see the output signal like this. So we'll put it into the XY mode, then we'll calculate how many squares the signal covers. So you can see it covers one square, one complete square, and voltage division knob is at 0.2. So you can say that output voltage is 0.2 volts. So you can write here the output voltage is 0.2 volts. So next we'll move the frequency, change the frequency to 50 Hertz. So we'll move the frequency to 50 Hertz, and now you can see the voltage increases. So voltage is increased. I will put the voltage division knob to 0.5, and now you can see it covers one complete square. So you can take it as a 1 into the voltage division knob of 0.5. So your answer will be 0.5 volts. So just write down the output voltage of 0.5 volts. Next we will go to the frequency. So we will make it 100 Hertz. So after making 100 Hertz, we can see the voltage has increased slightly. So you can see here there is one complete square, and beyond that 2 points, meaning that it comes out to be 1.4 into the voltage division knob, that is 0.5. So you can say that the output voltage comes out to be 1.4 into 0.5, that is 0.7 volts. So we'll write it here 0.7 volts. Next frequency is 200 Hertz. So we'll increase the frequency to 200 Hertz, and now we can see the output has slightly increased. So it is 1.8. So you can see 1.8 into 0.5, that is 0.9 volts. So we get 0.9 volts output at the frequency 200 Hertz. Next is 300 Hertz. So we are going to increase the frequency to 300 Hertz. So at 300 Hertz we almost got the same output, that is 0.9 volts. So 0.9 volts we'll write here. So we'll increase the frequency to directly to 1 kilohertz. So we'll increase the frequency to 1 kilohertz, that is 1000 hertz. So this is 1000 hertz, and you can see the output is increased. So this is the output signal. So it is increased. So it covers, we'll put it into XY mode, it covers two complete squares and 2 into this voltage division knob of 0.5. So it comes out to be 1 volts. So output for 1 kilohertz is 1 hertz. Next we'll go to the frequency 5 kilohertz. So we'll make the frequency of 5 kilohertz, and now we can see the output is same, that is 2 squares into 0.5, that is 1 volts. So we'll write the output voltage for 5 kilohertz frequency is 1 volts. Next we'll move the frequency to 20 kilohertz. So here the output remains constant, so you can skip the middle frequencies. So we'll directly go to the 20 kilohertz, and for 20 kilohertz you can see the output remains the same, that is 1 volts. 2 into 0.5, that is 1 volts. So after that the next frequency is 50 kilohertz. So we'll increase the frequency to 50 kilohertz. So this is 50 kilohertz. Now you can see the output has decreased slightly, a very slight change in the output. So it comes out to be 1 complete square and 4 points, that is 1.8 into 0.5, that is 0.9 volts. So 0.9 volts. So next frequency is 100 kilohertz. We'll go to the 100 kilohertz, and again you can see for 100 kilohertz your output has been decreased. So it is 1.4 into 0.5, that is 0.7 volts. So next frequency is 200 kilohertz. So we'll change this frequency to 200 kilohertz. Now we'll check the output, and output again it is decreased, and it comes out to be 0.5, that is 1 into 0.5, that is 0.5 volts. So for 200 kilohertz our output is 0.5 volts. So we'll again increase the frequency to 500 kilohertz. So for 500 kilohertz, see here the output is reduced, again reduced. So it is only 0.4 into 0.5, so it is reduced to 0.2 volts. And next we will go to the frequency of 1 megahertz, that is 1000 kilohertz. Again you can see the output voltage is decreased, and it comes out to be almost 0.1 volts. So it is a 0.1 volts. So this is the observation table for this common source field effect transistor or amplifier. So as discussed earlier with C amplifier, so your input is 50 millivolts. So V in is 50 millivolts, you can see here, and you got output for different frequencies. So in this voltage gain column, so this is homework for you, you have to do it, calculate it. So pause this video for a short while and take these readings on your notebook or any paper you have, and calculate the voltage gain by the formula AV is equal to V out divided by V in. So by using this formula you can calculate the voltage gain. So V in is same, that is 50 millivolts. So you can calculate the voltage gain V out by 50 millivolts. So, this voltage gain will be like this, and next you have to calculate this gain in dB. So, to calculate the gain in dB, you have to write gain in dB equal to 20 log of your voltage gain. Whatever voltage gain you have calculated from this formula, you will put it here and you will calculate the gain in dB by using 20 log of AV and write the gain in dB in this column. So, by calculating this gain in dB, you have to plot. Now, in this video, I will not share any graph plotting. So, you have to plot the graph by using the previous C amplifier lecture. So, by using this frequency versus gain in dB, you have to plot the graph and then you have to calculate the bandwidth of your FET amplifier. So, I hope you all understand the basic concepts regarding the FET amplifier. Thank you for watching the video. If you have any doubts, then let me know. Thank you.